Hello. So today I'd like to review midterm exam. I graded your midterm answers and I found some common mistakes and I had something to talk about to tell you. And you know what? Uh, the thing happened. I recorded the videos without turning on the mic. So I already explained like question one and question two. It took maybe like an hour. Uh, I when I try to upload those videos to YouTube, oh then uh, I I I I realized. Okay. Um. mm, so like I'm not going to type again here. It's okay. Let me think about what I talked in the previous version. So first, like you may have realized that homework questions are repeated every year, but still they have errors. They have errors because I do not solve them completely. I do not try when I make questions. I don't do the algebra. I just imagine it'll be easy, but actually that's not easy. So that is a bigger problem in the exams because I make new questions every year. This time, like so, then the main okay, 30 algebra is not a big problem. Anyhow, it's a waste of your time, but that will be a good exercise in the end, I believe. But the bigger problem is sometimes I have to do well in asking questions for you to answer well. Like for your learning, it's my responsibility to ask well, right? Well defined and clear questions is very important for your like a good answer from you, right? But question one is exactly the bad example. I did not do well in asking you what you have to do, and the algebra is also dirty. So even if you try the correct way, you will think, oh, something is not correct, not right. So I'm sorry about that. Let me explain what I wanted to do and what I expected. But because I did not ask it clearly well, it's my fault, my bad. Uh, Anyhow, the question is pretty simple. We have three regressors, one intercept, and two regressors. So let's think about like and here first I ask what is the full rank assumption? And of course that is about this expectation matrices. This expectations rank equals 3 because 3 dimension, or excuse me, this matrix should be invertible, which means the determinant is non-zero, right? And when specifically when there are two regressors with an intercept, you can write the relationship like this. So let me explain the intuition here. So variance of x1 is not 0. This means there is some variation in x1. In other words, x1 is not constant. In other words, x1 and the intercept are not multicollinear. So the first equation ensures that x1 and the intercept term are not multicollinear. Similarly, variance of x2 is not 0. This is about the relationship between x2 and 1. Finally, correlation between x1 and x2 should be not exactly 1 or minus 1, right? Shouldn't be perfect correlate. Like the correlation should not be perfect, right? That is about the relationship between these two regressors, right? To avoid multicollinearity between these two. So when there are three regressors like this, then you can simplify the conditions to these three lines. But it does not hold more than three cases, more than three regressors. So this is true here. And the correlation coefficient, using the definition of the correlation coefficient, you can rewrite the last condition into variance and covariance. Okay, like I think we have done this in an earlier homework. using like Cauchy-Schwarz inequality, blah, blah, blah. So what I wanted you to do is those three conditions, replace those three conditions with the variance and covariances of those variables we actually use, G, R, and I, right? But I realized that it's really complicated. But what still you can say something. For example, like the first thing, variance x1 is the first condition, x1 should not be, the variance of x1 should not be 0. X1 should not be constant. That means, so variance of x1 should not be 0 implies gi minus ri is not a constant. So this is more interpretable, condition, right? Similarly, like a variance of x2 not 0 implies ri minus ii is not a constant, right? That's also intuitive. The growth rate and the difference between the growth rate and the inflation rate should not be a constant. Like a growth rate, the real growth should change, right? Pretty much the same thing. And finally, the final thing, correlation between these two guys, not perfect, means correlation between G and Ri is not perfect, right? Because I is the common part. I believe, I don't know, like, so you have to do some algebra. Algebra is not, I thought it would be easy. And you can say this in the end, but the algebra is quite dirty, like, because you have to show this. But anyhow, you get the idea, like the correlation between these two should not be perfect, okay? So that was part A. Part B was easier. Part B was about exogeneity assumption. Part B, in the exogeneity assumption, you have done well. It's easy. What I wanted to say here is G and I do not need to be exogenous, because anyhow we are going to use their difference, right? So even if G and I are separately endogenous, still your regression may be okay, right? If somehow the correlation, the covariance are canceled out by each other, right? So that's what I wanted to say, right? What you like, so you have to distinguish what you are doing from your actual data, right? Very simple application of our results. And then additionally, I'd like to mention a few things, potentially confusing things. First, again, I have repeated this many times. Identification and sample size. In the identification argument, I'm asking if you can estimate the parameter correctly when you have infinite number of data. So finite sample, when you have finite sample, always you are going to have finite sample error. Random error happens in finite sample. But because we have infinite number of observations, we do not worry about the random error from the finite sample. So like, for example, sample error, sample mean can be different from the true mean. Even if true mean is 0, sample mean could be different, and vice versa. So that is a problem. So I want you to distinguish the difference between true mean, population mean, which is the true mean, which is the mean you can calculate when you know the true distribution or when you have infinite observations. On the other hand, the sample mean is the mean you calculate based on your data, right? It's only available in your data. But it could be different if your data happen to be different, if your data has some errors, right? Then your sample mean is definitely different from the true mean. And second thing, independence. Independence, and you know what independence means, but different notions of independence is used different places, like statistical independence and uncorrelatedness. Think about this. When I define the statistical independence, it means the full distribution function, joint distribution function, can be separated into distribution function of x and distribution function of y. And as a property of this definition from this statistical independence, you can say that the expectation of multiplication of gx and hy. So take any function on x and take another function on y and multiply them and then take expectation. You can simplify them into two separate expectations, right? No matter what these functions are, right? Like it can be linear, it can be quadratic, exponential, whatever, you can do this, right? So statistical independence is really strong and powerful. Meanwhile, the uncorrelatedness is milder. It only assumes this, right? If you multiply x and y and take expectation, then you can split them, separate them. So this is a weaker version of this result. Earlier, I could allow any kind of function, but now we don't allow any function, just direct multiplication, right? So uncorrelatedness is much weaker. On top of that, linear dependence and linear independence is also confusing. Originally the linear independence and dependence are in non-stochastic deterministic mathematics, right? Linear algebra does not think about stochastic situations, but we can directly extend the deterministic definition to random thing, like using probability 100%. So something should happen with 100%, right? So a random variable y and random variable x, random vector x and y should satisfy this multicollinearity condition always with 100%. Always they move together. So this is really strong. Of course, this is about dependence. If this fails to hold, then they are linearly independent. Okay. So even if two random variables are similar, still they are linearly independent. If they are not perfectly correlated but similar, then they are linearly independent. Okay. So this is strongest thing. Linear is like weakest, milder than uncorrelatedness. Okay. And also another thing here is independence in which dimension, right? So we have two regressors, a growth rate and like treasury bond rate. They are independent. Suppose that they are independent. Okay, that is one independence. But also, you can think about the independence, like last year's growth rate is independent of this year's growth rate. So these two are different independences, right? So first independence is independence between two different variables at the same time or for the same observation, right? But when you repeat the same observations, you can think about your first coin toss is independent of the second coin toss when you repeat sample. So this is basically one of the IID assumptions, right? So, and of course, IID assumption is everywhere in my course because it is obvious I don't mention that, but implicitly I'm assuming IID everywhere. So you don't need to worry about that. Mainly, you have to worry about the dependence between x1 and x2, dependence between two different variables, not across observations, right? That is another potential confusion you have here. And another idea, when I make up this question, I thought about this question too. So think about, I wanted to use real growth rate, real treasury bond rate, and also I wanted to use inflation as a separate variable. Is that possible? Can you identify this? think about this, right? So think about if this is identified, and like think about what is the identifiable condition. The answer is yes, it is identified, and this is identified if the standard regression is identified. So simply y on regression of y on GRI, not transforming the nominal variables into real terms. I just directly regress y on GRI. Then like it's like a structural model, and the reduced form model. In the reduced form model, suppose that you identify alpha tilde, beta tilde, gamma tilde, delta tilde, and epsilon tilde. Then you identify them under the exogeneity and full rank assumptions. And then if you identify them, you can identify the structural original parameters because this is their relationship. If you expand this term and this term, you can bundle, like combine I terms together so that the coefficient of I is like this. That means delta tilde is this guy, but beta and gamma are still good. So you only need to change like this. That means if you can identify this, you identify alpha 0, beta 0, gamma 0, delta 0. And the other way goes the same way. If you identify the original model, then of course you can identify this one by changing delta tilde this way. Okay, so maybe this is a better question now. I think I should have made this as the exam question. So that was just digression. And thank you for listening to this. It was my second recording. I will do the second question soon. Bye.